Right, how do we calculate the total impedance then, gentlemen? XC 1 over 2 pi FC 1 over 2 pi equals Tom. XL, Taylor? Two pi FL, 2 pi times 50 times equals. Wrong one. Well, I hope so. Is it 7 or 6? Correctly rounded as 7, is it? Okay, then, Nathan? So we got Z is equal to R plus XL minus XC J, and R is XL 37.7 minus 31.8. Okay. We don't need to do that subtraction in there. We can, you can just enter that in as a calculation in the conversion. Convert to polar equals what? 7.73 angle we in agreement, gents? All of you? Yep. And that's a 5, Don, right? Okay, so we calculate current V. Must be 2 yeah. Volume is 300. About, let's take that one off there and make that minus 49.73. Yep. Okay. So that's our calendar. Yep. C. Let's do C first. Are you talking about rearranging VS equal to VR a complex number for? No, you can't. No. Well, you can just use it. We're interested in V pellets are. The this calculated, and the transmission on just the capacitor. Yeah. So equals, and I like to put these in brackets. 38.9 and minus 49.7. C was 31.8. Angle, capacity. Look back at your diagrams. Angle associated with X. Let me take you back. XL positive 90, C negative 90. Alright? 90. You didn't say negative. Right? Yeah. So it's angle minus 90 degrees in there. How do we do this polar multiplication? Yeah, multiply the magnitude and angles. So 38.9 plus 31.8. Sorry, times 31.8. One, two, three, 7. That'll do. That's angle. Minus 49.7 plus minus 90. Time 9.7. Yep. So the voltage across the capacitor, despite you applying 300 volts, is 1,237 volts. Angle minus 139. That's that high because it's getting close to the two pipes being equal. Alright? The XL and XC are close to equality. Yeah? Now, what about V coil? We're looking at the coil that is a resistor and an inductor in series, and we want to know what the voltage across the coil is. If that was a coil, we can't get our meter in and measure just the voltage across the inductance or the resistance. We're just representing a real got some inductance. So what we need here, we can use Ohm's law, but it's got to be I times Z coil. How do I calculate Z coil? That's 5 ohms and this is 5 ohms. And XL was 37.7. Yeah. So XLJ. Just the resistor and the inductor here. That's 5 plus 37.7. 0.7 J ohms. Convert to polar. Someone can find place angle degree. 4 coil equals the current, which is 38.9, angle minus 49.7 degrees, multiplied by this impedance here, 38 angle 82.4 degrees. So we multiply the two numbers together, 38.9 and 38. One volts angle minus 49.7 2.4 circuit with 300 applied will have voltages of 1237 across the capacitor and 147 across the coil. Now you might say Kirchhoff's voltage law is not being obeyed. If we add together 1200 and some and 1400 odd, we don't get 300s. But if you added them together, including the angles on the rectangular form and added, you'd find that they do add up to 300 volts. Because remember, the two angles of those two are a long way from each other. The phase diagram is that VC and V coil are a long way apart. Okay? Yep. Any questions? Right, last little bit. Series resonance. At a particular frequency FR, F resonance. Yeah, when L equal to X. If we put that in, consider that in this formula, Z is equal to R plus XL XC out of that. If they're both equal. Z is equal to R. Yeah? So the only opposition to current at series resonance is the resistance of the circuit. The overall impedance is as low as it's ever going to be. Therefore, the highest possible current flows resonance. We can also say that VL is going to be equal to VP magnitudes. Angles will be 180 degrees in opposition to each other. Okay, so series resonance in a main circuit could possibly be very dangerous because the biggest current will flow at resonance, and therefore you get large voltages, even bigger in that last example, across the capacitor. So, problem. Coil has a 10 ohms. It's 120 Henrys. In series with a 60 microfarad capacitor. 120 volts. Find resonant frequency. FR, find the current at FR, and VL and VC. Okay. What fact can I use, do you think, to find the resonant frequency? What fact can I use? Yeah. At FR, XL is equal to C. How do I calculate X? Everyone agree with that? So it's 2 pi at resonance, 2 pi FL, and C with over 2 pi F, and that should have a little R in there for resonance frequency FR. Okay, now I've got to do some work to get the two FRs together and on their own. what happens if I multiply by I'll tell you what's a quicker way than this. It'd be much easier to see how this formula. What's the other form of XL? It is omega L. Remembering that omega is equal to 2 pi f, so if we can find omega, we can easily find f. So omega resonance is equal to times L is equal to omega resonance times C. Now, how can I get that L over that side, over the right hand side? No, this is omega resonant. What omega is at the resonant frequency. Remember, we know that omega resonant is equal to 2 pi f resonant. So if we can find omega resonant, find f resonant. Do you agree with that? All of that omega makes the maths easier. So how can I get that L down there? So we get omega r 1 over omega r LC. Now how can I get that omega back up the other side with this one? So how do I write omega r times omega r in normal? Omega r squared is equal to 1 over L. How do I get rid of the square? So omega r is equal to 1 over L. Root of 1 is 1. Yeah? What? If you do, if what you're saying is should this, yes, the application of that is that's equal to root 1 over root LC, yeah, and root of 1 is 1. Where that come from, right? But of course you don't have it. You can in a minute, Don, I'll put it back up in a minute. Get part of the time. Okay. So omega r is equal to root LC, which is 1 over square root of, what was L? 125 millihenries. It's 60 microfarads. Come on, let's get this resonant frequency. Get to finish it off between now. Hurry up! Let's say 0.2. No, rads per second. Right, now you've got to turn that over into LFR. Right, you'll stop there. You can finish that off between now and next week. and we'll start next week's session with the answer to that problem before we move on.